Investigation of curves, section 3, limiting behaviour. Video 3, oblique asymptotes. In the previous video, we looked at vertical and horizontal asymptotes. An oblique asymptote is a non-horizontal, non-vertical line that a curve approaches as x tends to plus or minus infinity. Now, when we're looking for oblique asymptotes, we can look for functions where the order of the numerator is 1 greater than the order of the denominator. So, for example, I might have x squared as the highest order term in my numerator and x as the highest order term in my denominator. Or I might have x cubed as the highest order term in the numerator and x squared in the denominator, and so on. Now, if this is the case, I can rewrite my y equals f of x term as y equals mx plus c, a linear term, followed by px over q of x, where the order of p of x is less than the order of q of x. And that allows me to deduce that y tends to mx plus c as x tends to plus or minus infinity, because this p of x over q of x term tends to 0. Let's have a look at an example. So, find the equations of the asymptotes of the curve with equation y equals kx squared plus kx plus 3x over x plus 1. Let's start by plotting it in GeoGebra. So I'll start by inputting my function. So my numerator was k times x squared plus k times x plus 3 times x, and then my denominator is just x plus 1. And it wants me to create a slider for k, so there I go. And now I can move, I can zoom out a little bit and then change my value for k, and you can see the behaviour of the curve and how it changes for different values of k. But it looks as if whatever my value of k is, I've got this diagonal line here, and it looks as if the function is tending to this diagonal line. If I zoom out a bit, you can see the behaviour away from the origin. It is tending towards that straight line. So now that we know what it looks like, how would we show the equation of the asymptote? Well, one thing that we can do is we can rearrange the function as shown before into y equals mx plus c plus a rational function. So I've spotted that in the numerator here, I can write it as kx squared plus kx plus 3x, and then I can add on a 3 and then take that 3 off again. So I've basically added 0 to the numerator. And then in the denominator, I've got my x plus 1. And now I can factorise this. So I get kx times x plus 1, that gives me my kx squared plus kx, plus 3 times x plus 1, which gives me my 3x plus 3, and then the minus 3 on the end, and then I can divide all of that by x plus 1. And now I can cancel. I should say that this is y equals here. So then that simplifies. This cancels with this cancels with this. So I get kx plus 3 minus 3 over x plus 1. And then I know that y equals kx plus 3 is an oblique asymptote. Now, I didn't have to do this by hand. I could have used my computer algebra system because there's a partial fractions function. Let's have a quick look at how that would work. So I'll put my expression in for the numerator was k times x squared plus k times x plus 3 times x. Put that in some brackets. And then divide by x plus 1, and then I can just type in partial fractions of expression 1, and it rewrites it for me as xk plus 3 minus 3 over x plus 1. So my kx plus 3 minus 3 over x plus 1 that I had before. So kx plus 3 is my asymptote. Let's plot that onto our graph. So y equals kx plus 3, and there we are. I can now vary k, and I can see that I've got this oblique asymptote to my function. In this video, you've learned what an oblique asymptote is and how to find equations of oblique asymptotes.